Okay, class, today we're going to continue with our Hess law. We're going to review standard enthalpies of formation, define lattice energy, and bond energy calculations. So like I said in one of the last play posits, there are several different ways we can go about Hess's law, and so we're just continuing on that course. The quest that goes with this video is 19C, Thermodynamics, first law. All right, so let's review standard enthalpies of formation. With standard enthalpy of formation, that is delta H naught with a F. F stands for formation. This is just the energy needed to produce 1 mole of a compound from its elements in their standard states. So in this table over here, we've got a bunch of values for the formation of those compounds. Some of them are negative values, meaning that they are favorably formed. That's exothermic. If you see a positive value, that is endothermic, an endothermic process for that formation. So we can remind ourselves that positive means endo, and negative is exothermic. Okay. And we also see here that the delta H of formation is 0 for elements in their standard states. We're talking about things like diatomic gases there. These are the standard states for those elements. So if you see something like O2, its delta H of formation would be 0 kilojoules per mole. Or if you also have just standard elements, so like something like just copper solid, and then you've got 0 kilojoules per mole. Okay. This equation up here, this is the big one. You've seen this before in honors. The sum, this means our sum here, the sum of our delta H of formation for our products minus the sum of delta H formation for our reactants gives us the enthalpy for the entire reaction, delta H reaction. Okay. We're also going to see some problems dealing with something called lattice energy. This is the energy required to break apart an ionic solid and convert it into its atoms into gaseous ions. So you'll see we start with our solid here, and then we split them apart into their elements. So we've got solid sodium and chlorine gas, and then we continue to add energy until they become the ion forms, so in the gaseous state. So we've got Na plus as a gas and Cl minus as a gas. So the lattice energy is the difference in energy between these two things. So the solid sodium chloride versus the gaseous form. Essentially what we're saying is that we are throwing so much energy into this thing that we are vaporizing it and measuring that amount of energy until we can determine the lattice energy. You won't see this too often, but it is good to know about it when you get to college level chemistry. This is very important for what's called atomic absorption spectra. It's really cool stuff. It's also related to your flame test, I believe. All right. So the Hess law version that we're going to look at. This is version 2. So when we have our reaction, we write down the values that we can find in the table. I'll give you a table. I know it says in the back of the book. It is usually in the textbook, but we'll give you a table. You add up the products, and you have to make sure you multiply those delta H values by the coefficients. It is proportional to the moles. Remember that delta H is always in kilojoules per mole. Kilojoules per mole. That's an area where a lot of people lose points on the test because they don't put those units kilojoule per mole. On the electrochem test, I was lenient about that. If you said kilojoules for delta G or delta H, I gave it to you. But on the thermo test, I'm not going to give those points to you if it's in the rubric. So make sure you say per mole. That is what they like to see because it's the formation of 1 mole of that substance. Anyways, step 2, you said you add up the products multiplying by any coefficients. Do the same with the reactant side. And then you do products minus reactants. So the sum of the products minus the reactants, and you will get your delta H of reaction. Oops, sorry. Delta H of reaction. So that's what it's equal to, the sum of delta H, HF of the products, and delta HF of the reactants. All right. Forgot my sum sign. There you go. Okay. So here's our first example. So we have 3 aluminums plus ammonium, I think that's perchlorate, ammonium perchlorate. And then we've got aluminum oxide forming with aluminum chloride. We've got nitrogen monoxide, and we've got water. So we use our equation. We want, again, delta H, and we've got delta H of our products minus delta H of our reactants. Okay, I always forget the sum sign there, so we're adding them up. So on our reactant side, we've got Al2O3, and we've got AlCl3. You make sure you put in the coefficients here. I didn't put the coefficients in for those because they're just 1, but we've got 3 times NO and plus 6 times my water. All right. And then we're going to subtract that from our reactants. And we've got 3 times NH4ClO4. And, whoop. Man, my pen's being a little funky today. There you go. Al, and then we're good to go. Okay? So delta H is equal to those values. Then we just need to plug them in. So let's find our values. We've got my parentheses. I'll do my bracket, I guess. I've got Al2O3, which is negative 1676 kilojoules per mole, kJ per mole, plus aluminum chloride, negative 704 kilojoules per mole, plus 3 times 90. Ooh, that one's got a positive formation, so that's not super favorable. That's okay. And then plus my 6 waters, 6 times negative 242 kilojoules per mole. All right. Close bracket. And then we need to subtract our reactants. So minus our reactants, 3 times my ammonium perchlorate, 295 kilojoules per mole. And uh-oh. What's the issue we see here? I don't see a value for aluminum. Well, if you remember back from the last slide, this is your standard state. What does that mean? That means this is 0, right? That is a pure element, 0 kilojoules per mole. So we actually don't even need to write in our value for aluminum because this is 0. Okay. So let's go into our calculators. Let's put all that in together. So parentheses, I like to do lots of parentheses, negative 1676, and close parentheses, plus negative 704, plus 3 times 90, plus 6 times negative 242. Okay? And I close parentheses. That's my product side. And that gives me negative 3562. All right. So negative 3562 kilojoules per mole on my product side. All right. So I got that, and I'm going to subtract. I'm going to do my other side. 3 times negative 295. I've got negative 885. So negative 885. And then I just subtract them. So negative 3562 minus negative 885, and I get negative 2677 kilojoules per mole. 2677 kilojoules per mole. And this is my delta H of reaction. Okay? And let's evaluate this. Is this going to be an endothermic or an exothermic reaction? You should have said exothermic because it's negative. This is exo. Okay. Here's another one. There are times where you may not be given all of the values, and you may have to calculate what the missing is. They'll give you delta H reaction. So sometimes all values are not found. We have to just be careful about what side things are. If delta H is on the reactant side, if it's on the reactant side, that means energy is being added, so that's endo. If you see delta H on the product side, that means it's exo. Energy is being given off, right? We're producing energy. So when we plug in our numbers, we've got to be careful here, because what's really happening is we've got a negative 2,800 kilojoules per mole. And that's equal, this is my delta H, right? That's equal to my products minus my reactants. So I've got my products, 6 CO2 plus 6 times H2O. All right. And I'm going to subtract my C6H12O6. All right. Plus my 6O2. Now we got to be careful. 6O2, what is that? That's a standard state. So this is going to be 0. So really, I can rearrange this equation and solve just for my C6H12O6. Okay. So let's plug in our numbers. We've got negative 2,800 kilojoules per mole. That's equal to 6 times negative 393.5 kilojoules per mole plus 6 times my water, negative 285.8 kilojoules per mole minus what I don't know, my X, 06. Okay. So then we could rearrange that so that we get my delta HF of C6H12O6. And we've got, now we have a positive 2800, right? We added to both sides, move things around. And then plus everything that I had right here, 6 times negative 393.5 and 6 times negative 285.8. All right, and we can go through, put that all in the calculator and get our delta H. I trust that you can put that in the calculator yourself. Go ahead and tell me what you get. All right, we go in our calculator. We've got 2,800 plus 6 times negative 393.5, close parentheses, plus 6 times negative 285.8. Oop, that should be a point. There you go. And we get negative 1275.8. If we're talking sig figs here, it looks like everything is in 4 sig figs. So we can go back negative 1276 kilojoules. Should have been your answer. If you didn't pay attention to sig figs, that's okay. But we do need to make sure we pay attention to sig figs in the future. All right. And now on to bond energies. So this is just a different version of the same equation. Delta H of formation values, using your delta H of formation values to find delta H of reaction are very much based on this principle here with bond energies. This is always a very confusing thing to students, especially if you've taken AP Bio before, and it's all because of our frame of reference, or even just in regular bio. They have this way of describing the breaking and forming of bonds, and breaking bonds, you're always told that breaking those bonds releases energy in bio, and that's because of the overall process is exothermic of releasing energy. But when we're talking about chemistry, we're talking about just individual bonds. Individual bonds take energy to break them. And this is because of that Coulombic attraction. Remember Coulombic attraction, that's your electrons and your nuclei being attracted to each other. Because of the opposite charges. So we have to break those electrons apart from each other to break that bond, right? So it does take energy to break bonds. Breaking bonds is endothermic. It requires energy. On the other side of things, forming bonds always releases energy because now you have a new Coulombic attraction between new atoms, and that lowers your potential energy, which causes a release of energy. So forming bonds is exothermic. Now, when you look at that process, if your energy of, so the delta H of the broken bonds, your energy of your broken bonds is greater than the energy of your bonds formed, then you will be in endothermic reaction, right? Because then you have a more positive number, a larger number on the left, minus a smaller number, it stays positive. Now, if you look at it this way, same thing. If we go the opposite direction, if the bonds formed are of greater energy than the bonds broken, you get in a small number. This is big minus small, which is positive. And then this is small minus big, and you get a negative number, right? So this will be negative. If I can move this around, I can't. Anyway, this will be positive. This will be exo because it's negative. All right. So when they're talking about that process, the processes in bio where breaking bonds releases energy, technically they are correct, but what they don't ever point out is that it's forming new bonds, and that energy is larger than the bonds being broken. So it is an exothermic process, but they never talk about the bonds being formed. Breaking bonds absorbs energy, and forming bonds releases energy. Okay? So let's do our one example with it. Here we want to calculate the change in energy that accompanies hydrogen gas and fluorine gas becoming HF. Okay? So we have to look at our balanced equation. All right, if we wrote this as a diatomic molecule, we can actually draw these Lewis structures and figure out which bonds we are breaking and how many. So we only have one of each of these, so we've got one H bond, H bond, and one fluorine-fluorine bond. But the trick here is that we've got two HF bonds that we're forming. So we're forming one, and then we're forming another one for a total of 2, right? So when we do our energies of the bonds broken minus the bonds formed, we have all of our bonds being broken. We have 2 bonds being broken. So we've got 432 kilojoules per mole plus 154 kilojoules per mole. And then we have to subtract 2 times 565 kilojoules per mole. Okay. So when we add that up, we've got 432. Why won't my calculator turn on? 432 plus 154, and we get 586. And we also have 2 times 565, so 1130. Okay, so let's evaluate. We've got 586 kilojoules of energy being spent on breaking bonds, and we will be forming 2 HF bonds, which releases 1100, a little over 1100 kilojoules per mole. Take a moment and evaluate. Will this be endothermic or exothermic? All right, before we even did this calculation, you can just look and see that 586 is less than 1130, so the bonds broken. So broken is less than formed, which means this should be exothermic. You can even check it based on the sign. 586 minus 1130, we get negative 544 kilojoules per mole. You can see that negative sign. Boom, that's where that negative sign comes from. This is an exothermic reaction. Sweet. Alrighty. That is all for today, I believe. Oh, actually, I just had this little chart to summarize. Let's summarize this in class. We can summarize the different kinds of H in class together. That'll be our recap for this video. That is it. Okay. Have a great day.